Hello and welcome to the second of a video series highlighting the fundamentals of the study of statics. This video will be talking about force vectors, which is chapter 2 in the book if you're taking BMME 160 at UNC Chapel Hill. And this is a really fundamental topic. Again, there's a lot going on the page. Try not to let it intimidate you. We're going to cover it at a slow pace without letting the video exceed. I'm aiming for 15 minutes here, so hopefully it won't go on too long. It's a very fundamental topic. If you don't get this, you got to make sure that you work out what's going wrong and what your misunderstandings are before you move on. Without a solid understanding of vectors and how to manipulate them, you're going to struggle with the rest of the course. It's really the one fundamental element that you need to really understand coming into this in order to move forward. So in terms of quantities, there are two types: a scalar quantity and a vector quantity. A scalar quantity only has a magnitude. Things like temperature or anything that you can sum up in a number. So it's 70 degrees in this room approximately, but there's nothing more. It's just a magnitude. In terms of vector quantities, you have not only a magnitude but also a direction. So a magnitude is a subset of a vector, but it's not the only facet. You also have a direction. And to indicate a vector quantity, I think I showed it in the last video in terms of Newton's second law as this little half arrow above vector quantities. So force is a vector quantity. It's something that you apply, and you can quantify that in terms of newtons as its magnitude, but it also has a direction. My force on this table is down, however you choose to specify that with a coordinate system. Mass here is the scalar, so I struggled so much to come up with another example of a scalar quantity, but here one is. Mass is a scalar, and it scales. So when I think of a scalar quantity, I think, oh, it scales the acceleration. It's a product. Usually you see it in the product form. Sometimes you could see it in division, but division is really a form of multiplication. It's scaling some other quantity, and acceleration here is the quantity it's scaling, which is not just a magnitude. There's also a direction. Which way are you accelerating? Common vectors that you've seen before outside of equations like this in physics 116, or I'm sure you've seen some vectors in math 233. The standard basis vectors I, J, K should be fairly familiar, and those are the standard basis. They actually make up what's called the base of the third dimension, R3. And we'll come back to that further. That's really important when you start talking about forces and force vectors in 3 dimensions. Here, I just want to, notation is key here. You have either the half arrow or the little caret hat thing. People call it I hat, J hat, K hat. It doesn't really matter which notation you choose. Pick one, stick to it. Typically in physics, you'll see the hat over the standard basis vectors, especially. And some other special cases. In this course, I think the primary thing you're going to see is this half arrow. Here you can see that the magnitude of something can be specified either as just the letter itself, so here F for force, or you can put the absolute value of, it's not really the absolute value, it should be read as the magnitude of vector F. But you can think of it like an absolute value because that negates the direction that's been specified. It's really just the value of F. So either the letter itself or 2 bars on either side of a vector is just the magnitude with the direction thrown out the window. And another way that you'll see this in your book is a highlighted, a bold letter is going to be a vector, whereas a non-bold character denotes just a scalar quantity. So what is a vector on paper? In a geometrical sense, it's an arrow. You have a tail and a head to a vector with a name, like we've been saying. Now you can scale it. either with something out front, much like acceleration has been scaled by mass. You can scale it with something, a number, a scalar quantity. So think scaling again. Here we've scaled it with -1, which flips the vector. Now, floating vectors are kind of a hard concept. It doesn't matter where, and we will put it in, reference to some sort of a rectangular coordinate system or even other coordinate systems that exist. It doesn't matter where the vector is for it to be equivalent. If I have k here, it's the same as me drawing k here as long as it's parallel and of the same length. That's something that you should really think about. So here, we've multiplied it by a -1, and that's flipped the direction, but it's the same length, and it's still parallel to the original vector. Here we've multiplied it by some scalar quantity that's less than 1. It's still parallel to the original k, but it's been scaled back so it's smaller in size. Now there are multiple ways of adding up vectors, so we typically start by thinking about it in the geometric sense. How do we add things up? Usually, in the scalar sense, 2 plus 3 is 5, and that holds for collinear vectors. So when you have two vectors in the same linear arrangement, they're parallel to each other, you can say, a plus b does equal c, where c equals b plus a. All those things still hold, and they're just simple algebraic addition. So the geometric procedure, I suppose you can follow in the case where they're not collinear, is either the triangle rule here or the parallelogram law. I don't know why this one's a law and that one's I think they're both rules. The book calls this one a law and that one a rule, but that seems silly to me. The concept here for the parallelogram law is probably a bit simpler than the triangle rule. I've used both pretty much interchangeably. It just depends on which one's easier for the situation that you're looking at. Things can get kind of complex. So let's say we're adding a and b to get c. These are just made up vectors. A goes this way, b goes this way, and again, they can be floating anywhere in two-dimensional space. I've restricted it to at least 2 dimensions here. We're not going to worry about third or any other dimension. So what do we do here? We draw a dashed line or a line from the head of A parallel to B, and do the same thing off of the head of B, and where the two lines intersect and form this parallelogram, you have what is the head of the resultant. So if you add A and B together, you get C, which is a resultant. Again, by drawing lines parallel to the two sides and making this parallelogram with the resultant being the diagonal. In the triangle rule case, what you do is say, oh, I'm adding force 2 to force 1. And again, this could be anything. You could say vector A to B to get C. The fact that I'm just going to try to start calling things forces so that you get used to it, because you're not going to be adding random vectors in this class. You're going to be adding forces. So here, an important thing to notice is that since we're in a triangle, we're going to define the angles within it, much like we always have with theta sub the name of the opposite side. So 1 corresponding to the opposite side of the triangle being F1, or corresponding to FR on the opposite side, and theta 2 corresponding to the 2 over here. And what we do here is we take the tip or the head of one vector and line it up with the tail of the other. It doesn't really matter in what sequence. Either way you do it, it actually ends up being the same vector. It might not be in the same space, but again, if we're not talking about a coordinate system, and even if we are, it's the same vector at the end of the day. As long as it's the same length and parallel, no matter where it's floating, it's the same force. And of course, it matters where it's hitting an object, but even still. Now, just some geometrical rules or laws, actually. The law of sines and the law of cosines, the law of sines and the law of cosines can be applied to any triangle where these parameters are given as such. That's just something you should keep in mind. Some problems, they won't really require this. There's always 5 ways to solve a problem usually. But this is something to keep in mind. It can really simplify your work, especially the law of sines. It's very simple and easy to remember. You just, keeping in mind that the force and the angle are always in the same composite quantity. The law of cosines is a bit harder to remember. Of course, it's fairly easy to derive. I'm not going to do that here. You can do that on your own time. So what these things weren't done with respect to any coordinate system. So when we talk about the rectangular coordinate system, which is the coordinate system we're most familiar with, what happens? How can we break down a vector? Now, first things first, when you have a coordinate system, you want to specify what are your positive directions. And that's something I do by having a little tiny arrow, not to be confused with a vector, on the end of my axis. So this one doesn't have one, that's the negative side. This one does, that's the positive side. You could also put a plus in a circle next to this x and a plus and a y next to this up here to indicate that those are the positive things. So here we're looking at a force vector F, which extends into the first quadrant of this rectangular coordinate system. And we will move on from 2 dimensions up into up into the, there we go, up into the 3rd dimensional case, but we're going to focus on just R2 here. And we can break it down into its respective components, and this should be nothing new. We talked about this in Math 233, which you should have taken by now, or I don't know if it's a prerequisite. Either way, you should have seen this in Physics 116. So this should be nothing new. Breaking it down into its components, you see something that's projected onto the x-axis and projected onto the y-axis, and you can use basic trigonometric relations to figure out what's the magnitude of f, what is the angle with respect to the x-axis, which is always our reference when we're doing things. So I say here we have phi or phi, however you choose to pronounce it, relative to the positive x-axis, which is where that always is. And that's something important to note. So, that's fine and well, and we can, refer to this vector in terms of its components, its respective components along that. Keep in mind here that this line here drawn up, these perpendicular lines that drop down off of the head of this vector f are equivalent. So Fy over here, the magnitude, so we could draw the absolute values of the bars around this guy and call it the magnitude of Fy or the magnitude of Fx here, and those are equivalent in terms of length. So what happens when we have, 2 vectors or 3 or 4 or 5 or 6, and in this class you really will probably have that many in a problem, up to 5, 6, 7, even 8 in one coordinate system at one point, that you need to figure out, how do I add all these up, much like we added up the vectors over here to come up with our resultant force. So here we can split up our 2 vectors that we have into its respective components with this nifty little notation here. If this is F2 and this is F1, we have F2y and F1. That's not right, excuse me. That should be F1y. That's wrong, pardon me. This is F2y. I don't know why I drew that. Either way, we can break it down into its respective components, and then you could geometrically say, okay, let me draw F2y parallel over here and a line over here and come up with the resultant. And that's perfect. That's what you should do geometrically on paper. But in terms of math, you can find the resultant's x component by summing the forces along the x-axis, or the components along the x-axis. So if we add f1x to f2x, note one of these is positive and one of these is negative, f2x being a positive quantity and this being a negative quantity, it goes in the negative direction. How you deal with negatives is up to you, but you have to account for them or your answers are going to come up differently. And then the y's. Again, I apologize. This is supposed to be f1y. It's just an error on my part. And then the magnitude of the two will be, the magnitude, of the resultant when you add them together is going to be the radical of the, what's this called? Added in quadrature is another term for this. Yeah, that's the official name. So when you add the 2 components squared under a radical, that's called adding it in quadrature. Which I'm sure you heard ad nauseum in Physics 116 with respect to uncertainty. Over here, this is a way to find I just forgot to mention it, a way to find phi or phi over here with arctangent with respect to that. And that's just a basic geometrical thing. Oh no, that's with regards to this one. So in when you come up with frx and fry, you can take the arctangent of the ratio between the two and come up with your own phi or phi for the resultant, which is the angle, much like we defined it up here, relative to the positive x-axis. So you have not only a magnitude and direction, those are the two things you need to have a vector, and you're done. That's all you really need. You've specified the resultant force to the full extent. We have a few more things. Pardon me for having the video go so long. I'll try to do better in the future. So the concept of a unit vector here is really key. It's really just to specify the direction. When we call it a unit vector, the name unit is derived from the fact that it has the length 1 or the length unity. Usually I use a U to describe it for unit or unity. It doesn't have any units because it's really just the vector itself. It's in the direction of this vector, say f, divided by the magnitude. So the only thing that really stays is this hat, the direction. So it has no units. It's f over f. The magnitudes cancel. The only thing you're left with is the quantity 1 in the direction that the force was initially, and examples of this abound. Most importantly, really, in mathematics is the standard basis vectors, which again form a basis for R3 in terms that you can describe any vector as a linear combination, and I know I'm using linear algebra terms here, but bear with me. You can describe any vector in R3 as a linear combination of the standard basis vectors by simply scaling them by the components. So if we have ijk in the third dimension in the rectangular coordinate system and the Cartesian system, you can say, well, the I hat here is scaled by fx, which is, for this particular vector, the component that's projected along the x-axis. If you're unfamiliar with this, just to review, we usually say xyz and ijk with their respective axes, and we look at it usually from the first quadrant of 8. Again, here in the third dimension, it's nice to have an arrow on the positive end, and usually I dash out the negative end because it gets too complicated to have that much going on at once. So if you want to look at it yet another way in terms of the unit vector, you're scaling the unit vector by the magnitude to find. So if this is the direction and that's your magnitude, you have a full vector. And that's interesting. Now, in terms of a position vector, this is something that's key, especially in the three-dimensional case. You really have to understand this. And I'm going to bring up another notation here that you may or may not be familiar with. A unit vector is really the ratio between the position vector, which is just a vector that points in the same direction as the force, the original force or vector, and the unit vector divided by its own magnitude. Again, it has to be, by definition, over here in order to be a unit vector. So this is just saying that the unit vector and the position vector for that particular force point in the same direction. So let's say a force passes through points A and B in whatever coordinate system you're in. Let's say we're in the rectangular case. We can say B minus A or A minus B, it doesn't matter, as long as you negate whatever negative sign, however that comes out, and you get the same quantities no matter what. As long as you're consistent with saying B minus A, B minus A, B minus A, or A minus B, etc. With the coordinates that you have, you end up getting a description for the position vector, which is 3 numbers. Now, I frequently use this less than, greater than symbol in order to come up with those 3 coordinates. And to specify it's a vector, usually when we have a coordinate like just a point, we put normal parentheses. But to specify that we're describing a vector here, usually I use the less than and greater than. That's not something that's necessarily required for the class. It's just a nice notation in this case. The last, and I promise you I'm I'm disappointed at how slow I'm going here. The very last thing we're going to talk about is the dot product, which is, again, review from Math 233, and even from maybe Physics 116. I don't know how much this came up. It definitely came up in Physics 117. So the dot product of two vectors is equal to the product of the magnitude of each vector and the cosine of the angle between them. And I just generally drew the situation we're describing here. And really what that means is you have to add the products of their respective quantities to get the same value as the dot product. It's not a vector. That's something you should note. When you take the dot product of two vectors, you get a scalar out. That's just going to be a number. What is this really useful for? If we're looking at a situation like this, it doesn't really matter which one you're looking at. You can, and I know this is confusing here, you can end up finding the angle between the two, and that's really the primary use, or vice versa. You can use this equation in either direction. Here, I've just wanted to note I used arc before in terms of, here we go, arctangent to find the angle of the resultant force here. I wanted to note that you can use either notation, either a -1 or arc in front of cosine, not both. So either you say cosine to the, and I know this is not right, it's not really to the negative power, it's denoting an inverse function. So either one of the two of that is equal to cosine. Final concept to touch on, concept of a projection. We've already talked about it up here. The projection of this guy onto the, say, x-axis on either of these situations, or either of these pictures here, is the projection onto that axis. So you just drop down a perpendicular line, and then that's your projection. That's something you can look at in the book. It's not, I mean, it's an important concept, but I'm trying to highlight the very most important concepts here. Coordinate direction angles, also, you can take a look at it in the book on page 44 and 45. Important, but not necessarily something you should spend all your time freaking out about. There'll probably be a couple of homework problems. It's not something that's necessarily going to come back and haunt you. It's nice to know, but it's by no means priority number one. If I had to point to priority number one, it would be getting very comfortable with this idea of dealing with multiple forces, adding them up, and finding a resultant force, and being able to describe it in terms of the angle that it makes with the positive x-axis, and its, finding its magnitude. Those are the things I would really worry about. Getting comfortable with the notation's another thing too, because there's a lot of it, and it's not easy if you're not familiar with it. All right, that's the second video. Stay tuned for the third video coming shortly.